past a tall building, a bridge, or even a staircase, and you are actually walking past triangles in disguise. Architects rely on them because triangles don't wobble. They hold their shape no matter what. Today, we are going to uncover the secrets of the world's most dependable geometric partner, the triangle. Let's start by talking about how we can construct a triangle. Can we construct a triangle using only a compass and a ruler? No protractor, no angles given? Think of your tools as partners in a mystery. The compass is the detective. It follows the clues of distance. The ruler is the reporter. It measures the exact length, so the detective can work accurately. First, let's start by giving the ruler one task. Mark a line segment AB of the exact length needed. Then the compass gets two clues: the lengths of line segment AC and the length of the line segment BC. You must be knowing that a circle is not just a round drawing. It's every point that sits at exactly the same distance from the center. Every point on circle A is a point that is exactly the right distance from A. Every point on circle B is a point that's exactly the right distance from B. When these two circles intersect, that is the only place where the third vertex C can exist while satisfying both the distances. When there are two intersecting arcs, there are two possible triangles. They look like mirror images of each other. So the compass and ruler are not just drawing tools. They are precision instruments that help us construct triangles using accurate lengths and logical deduction. Sometimes the intersection leads to only one intersecting arc, which gives us a tangent that leads to exactly one triangle. In the case of no intersection, it means that a triangle with these side lengths is impossible. Now let's talk about the types of triangles. Let's take some real-life anchors with this. Now that we can construct a triangle, we will try to classify it just like the architects classify the beams or the supports. With regards to the sides, we can classify the triangles as equilateral, where all sides are equal, stable and symmetric. You can think of decorative lampshades or those triangular road signage boards. Equilateral triangles also have equal angles. Next classification is isosceles, when the two sides are equal, steady and balanced, like the symmetry in many roofs. Then comes the scalene triangles with no sides equal. Scalene triangles are not actually flexible, they are just very common and are used in scaffolding everywhere. When we classify the triangles by angles, then we get acute angles, where all the angles are under 90 degrees. You can remember acute angle triangles as the gentle triangles. Then we have the right angle triangle with one right angle, which measures 90 degrees. They are the heroes of every staircase and ladder. The right triangle is a key in measuring the heights. We will see its Pythagoras connection later. Then comes the obtuse angle triangles, where one angle measures more than 90 degrees. They appear like the stretched out triangles. Every triangle you ever see fits into both a side category and an angle category. Let's delve into the angle sum property. There is a very beautiful characteristic of triangles. You take any triangle, tiny, huge, perfectly drawn, or casually sketched. You stretch it, you shrink it, you slant it, its angles always add up to 180 degrees. Always. This is why triangles are used to measure distances in maps and construction. If you know two angles of a triangle, the third one reveals itself automatically. This principle is used in surveying and navigation. Let's talk about the exterior angle property of a triangle now. Imagine extending one side of a triangle. The exterior angle that appears is always equal to the sum of the two opposite interior angles. This is one of those results that feels like a magician's trick, but it's pure geometry. It also shows that an exterior angle is always greater than either opposite interior angles, explaining why the ladders or supports always tilt at some predictable angles. Let's now move to a very interesting triangle property called the triangle inequality. Imagine three friends, A, B and C. They decide to meet. A walks towards B, B walks towards C and C walks towards A. But there's a catch. A can only meet B if the path from A to B is shorter than going A to C, then to B. The same must hold for every pair. In geometric language, the sum of any two sides of a triangle must always be greater than the third side. If this condition fails, the three friends won't meet. They line up in a straight line and the triangle collapses. Hence, a triangle is only possible if all three inequalities hold. Let's put it all together now. So here's our tale of three intersecting lines. The compass detective shows where a triangle can and cannot exist. Once constructed, triangles come in many types, each with its own personality. Their interior angles always sum to 180 degrees and the exterior angles expose the hidden relationships. And the triangle inequality ensures that the three sides can actually meet and form a triangular shape. All these properties give triangles their strength and stability. This is why architects love them. And once you understand triangles, you start seeing them everywhere. Not just as shapes, but as the quiet logic that holds the world together.